Right, we're going to look at amines today. So it's a new class of compounds. First of all, before we look at amines, we're going to look at a substance that you have come across before, and that substance is ammonia. So we know the chemical formula of ammonia is NH3. Let's try drawing it. So we know that it's got this sort of shape. Remember, this bond here is going into the paper. This bond here is coming out of the paper. This bond here is in the plane of the paper. And we'll have a lone pair there as well. Okay, so we've got 1, 2, 3 bonding pairs and 1 lone pair. That's 4 pairs in total coming from a central atom. When you've got 4 bonds in total coming from a central atom, that shape is tetrahedral. However, these are not 4 bonding pairs. This is 3 bonding pairs and 1 lone pair. Therefore, we don't call it a tetrahedral. We call it a trigonal pyramid. So you would have done this in topic 3 back last year. So we know that a tetrahedral, with a tetrahedral, obviously this is not a tetrahedral, it's a trigonal pyramid. If it was a tetrahedral, the bond angle would be 109.5. Remember, that's the key bond angle that you learned the formula of. And if you've got a lone pair of electrons, because that lone pair of electrons is pulled in closely to that highly electronegative atom, what it's going to do is, that lone pair there, it's going to repel these bonding pairs of electrons more than each bonding pair would repel to each other. So lone pair bonding pair repulsion is greater than bonding pair repulsion. What that means is about this whole molecule is that these bonding pairs of electrons get pushed in towards each other because this lone pair is going to repel them downwards. And my rule of thumb is, if you've got 1 lone pair of electrons, you take 2.5 degrees off the bond angle. So this bond angle here is not 109.5 because it's got 1 lone pair of electrons. We take off 2.5 degrees, and that is 107 degrees. If there were 2 lone pairs of electrons, for example in water, you would take off 5 degrees because 2.5 times 2 is 5. We've got a bond angle of 107 degrees there. Okay, so that's ammonia, and that's the structure of ammonia. And now we're going to level up the structure of amines. So another way of representing ammonia is to draw the flat representation. Obviously we know it's not flat, but often you might see it like that, and that will be an acceptable way to draw it in the exam, unless you're specifically asked to draw it in 3D like this. So we've got ammonia here. Now, if we replace one of those hydrogens for an R group, now let's just recap what an R group is. So an R group could be a CH3 group. An R group could be a CH2, CH3. So it could be a methyl, it could be an ethyl, or a propyl, or a butyl, etc. So that R group is a collective term, remember, for anything like this. Now, this isn't ammonia anymore, because I put an R group on there, like CH3 or CH2, CH3. That is what we're calling an amine. And because it's got 1 R group, it's a primary amine. This is an example of a primary amine. If this is a primary amine because there's 1 R group, and this is a secondary amine because there's 2 R groups. And a tertiary amine with 3 R groups. Okay, now next point to note that amines are very reactive. And there's two reasons why they are very reactive. And we're going to come back to those two reasons in a little bit. Because they are very reactive, it means that we can use them to make different things with. So that's really important there. Now, when we're writing down a primary amine, sometimes you might see this. A 1 there with this little degree sign. That just means a primary amine. So secondary amine, you might see this 2 with a little degree there. Or tertiary amine is 3 with a little degree sign there. That's what that means. Now you've come across primary, secondary and tertiary alcohols as well. So this is how you would decide whether something's a primary or secondary, tertiary amine. Now what we're going to do now is we're going to name amines. So a little subtitle there, naming. So let's have a go at the first one. Nice simple one. CH3 NH2. We can see straight away, because there are 2 hydrogens in one R group, it follows this pattern here. 2 hydrogens in one R group. So we know it's a primary amine. This is a primary amine, and we've got a CH3 group. Remember, a CH3 group is a methyl group. So if this is a methyl group, and it belongs to the family of amines, then the name of this, obviously, is methylamine. If you've got CH3, CH2, NH2, it's ethylamine. And another way to write ethylamine would be C2, because there's 2 carbons there, H5, 3 add 2 is 5, and H2. Again, that's just another way of writing ethylamine. Alternatively, you could draw it. Again, ethylamine here. This is a primary amine. So we'll call that an alkyl group. So the likes of methyl, ethyl, propyl, they're all examples of alkyl groups. It comes from the word alkane, you see, alkyl group. However, sometimes you've got like a benzene ring. So here's a benzene ring with a amine group on it. Now this one would be called phenylamine. Whenever you've got a benzene ring attached to a functional group, we'll call that a phenyl group. That's PHENYL. So this is phenylamine. So we've got ethylamine, methylamine, phenylamine. Okay, so those were examples of primary amines because there was one R group attached. Oh, hello there. That's a nice surprise. Yep, are you going to leave us alone? See you later. So, the next one that we're going to look at is a secondary amine. So, we've got this chemical formula here. Now, we know this is a secondary amine because there's 2 R groups. And these R groups are the same. They're both methyl groups. There's 2 of them. So it's dimethylamine. If, however, you've got 3 R groups, so for example, if they're ethyl groups, that's an ethyl group there. Then that would be 3 of them, so that's tri. ethyl amine. Okay, sometimes though these groups might be different. So if they're different, let's have a look what happens. So we've got a methyl group, and this is 3 carbons, that's a propyl group. So the name of this is, it's methyl, there's a methyl group, propyl amine. So that's methyl propyl amine. It's not propyl methyl amine, and that's because M comes before P in the alphabet. Okay, so we've got a secondary amine here, a tertiary amine, and a secondary amine, and some primary amines there. That's how you would name those. Let's have a look at the shape then. So we know that the shape of ammonia is like this. So that can tell us about the shape of an amine. So we can copy the shape of ammonia here. So here is an amine. Just made a mistake there, I've added too many bonds there. Can you see nitrogen there? Just spotted that. That hamster was just distracting me. Except nitrogen there. Remember, nitrogen is in group 5 of the periodic table. So that means it needs 3 more electrons. This is why I know I made a mistake. It needs 3 more electrons for a full shell to make 8. So it can only bond 3 times. And now I've started to put 4 bonds here. 1, 2, 3, 4. So that cannot be right. Yeah. So an amine, the nitrogen on the amine must only have 3 bonds to it. So it's 1, 2, 3. We'll just draw this flat. This is the sort of general structure of an amine. Now I've done this flat here, but we do know, don't we, that this bond angle here is, it would be, if you work this out, you've got probably a lone pair of electrons on here, 3 bonding pairs. If it was a pure tetrahedral and there was 4 bonding pairs, it would be 109.5, but it isn't because I've got a lone pair, so we take 2.5 degrees off that, just like we have done over here. So 109.5 take with 2.5 is 107 degrees. So the bond angle in an amine is the same as what it is in ammonia. Now, we know that nitrogen is the most electronegative atom in this molecule. So we can write delta negative on here. Now what that does is that pulls the electrons towards the nitrogen, which means that this would leave this delta positive, and pulling these electrons towards nitrogen here, pulling those electrons towards nitrogen there. That is delta positive, and that is also delta positive, and that just gives an indication of the reactivity of that. Now, what we're going to look at now is we're going to look at a bit of hydrogen bonding. So what I can do now is I can draw 2 molecules of an amine and draw a hydrogen bond between one molecule and another. So let's have a go at that. Now the amine that I'm going to pick is just methyl amine, which is this one here. I'm going to draw the hydrogen bond in between 2 molecules of methyl amine. So we've got a hydrogen bond here between two molecules of methylamine. So you get a mark for showing the lone pairs of electrons, the dotted line between the highly electronegative atom nitrogen and hydrogen, and then the examiner will be looking for you to draw these atoms in a line as well. Now, yes, hydrogen bonds are fairly strong, but this hydrogen bond here is not as strong as a hydrogen bond between two molecules of methanol, and I'm going to look at why that is now. So we've got methanol here. So I'd say that is strong, yeah, but that is not as strong. Let's have a look at why that is. Well, the first thing is, it can't really be much to do with the relative molecular mass of the compounds, because the relative molecular mass of methylamine, which is this stuff here, the MR, is 31. If you add that up, and the relative molecular mass of methanol is 32. So those are more or less the same, those two there. So it's nothing to do with that. It has to be to do with this atom here, nitrogen, and this atom here, oxygen. Now, you can look up the electronegativities of oxygen, and what you find is oxygen, the electronegativity of it is 3.5. However, the electronegativity of nitrogen is only 3.0, so there's a bit of a difference there. So nitrogen has a lower electronegativity than oxygen. So if we draw dipoles in here now, what we'll find is if the electronegativity of oxygen is higher than nitrogen, then the hydrogen bond is going to be much stronger. And if the hydrogen bond is going to be much stronger, it's going to take more energy to overcome those hydrogen bonds. Therefore, the melting point and boiling point of this structure here is going to be higher than that melting point and boiling point of that structure there. So I've got the melting points and boiling points here. So I'll give you the boiling point. So the boiling point of methanol, I'll just write BPT, it's shorthand for boiling point, is 267 Kelvin. Beg your pardon, wrong road. The boiling point of methylamine is 267 Kelvin, but the boiling point of methanol is higher, which is 338 Kelvin. And that's because of the stronger hydrogen bonds between molecules of alcohols compared to amines, because oxygen is more electronegative than nitrogen. Okay, so you find that actually this stuff here, methylamine, is actually gas, yeah, whereas methanol is actually a liquid at room temperature. And you might have heard of how amines smell. Now, amines have got a characteristic smell. Amines, the smell of like rotten fish or flesh, actually. It's a horrible smell. It's like a horrible, fishy, rotten smell. And that is basically because when like a dead fish or some flesh rots, it's actually amines that you're smelling. And the reason why you're smelling amines because meat is made up of proteins, and when proteins decompose, they produce amines. So that's where that rotten smell comes from. Anyway, little interesting fact there for you. Now we're going to look at solubility as well. So amines are relatively soluble, and let's have a look at why they're soluble. Again, it's to do with hydrogen bonding. So we can see a hydrogen bond here between an amine and water. Because you've got hydrogen bonds between amine and water, it means that amines are soluble. Okay, now before we move on to the reactions in a bit more detail in the next little subtopic of the lesson, let's just look at why they're reactive first of all. So to decide whether or why they're reactive, let's draw this structure out here again. This methylamine, but I'm going to show all the bonds this time, including those carbon-hydrogen bonds. So let's ask ourselves why these are reactive. So we need to look at the structure to decide why that's reactive. So first thing is, we've got highly electronegative atom here, this nitrogen here. So this highly electronegative atom with a lone pair of electrons can react with an H plus ion. So you can see here we've got a curly arrow, like that. So that's one reason why they are reactive. The next reason why they're reactive is nothing to do with the nitrogen here. Well, it's a consequence of the highly electronegative nitrogen, but because that highly electronegative nitrogen pulls electrons away from the carbon here, it leaves the carbon very, very positive, which means that amines can act as a nucleophile as well. Or I should say, so electron deficient carbonate when the amine is acting as a nucleophile. So it can actually attack the carbon as well. Okay, so what we've got there is we've got new class of compounds. We looked at ammonia here, why the bond angle of ammonia is 107 degrees. We learned about primary, secondary and tertiary amines. We'll have to name primary amines. Amines with a phenyl group. Name secondary amines, and then I think the hamster ran across the page. Naming tertiary amines, why amines smell of fish or rotten fish, and why amines have a lower melting point and boiling point than alcohols, and why amines are soluble. And a little hint there for what we're going to do next, actually, of why they're reactive. So that's basically 28.1 done.